When you look into a mirror, another you looks right back. It's not a version of you living in a parallel universe behind the glass. It's simply your image. And reflections aren't limited to mirrors. On a perfectly calm lake,
It was so clear, Jenny. It looked like there were two skies, one on top of the other.
in this episode, we're going to uncover the physics behind that symmetry by exploring how plane mirrors form images. When a plane mirror forms an image, how are the image's position and size related to the objects? To find out, let's run a simple experiment. Start by placing a large sheet of paper on the table. Stand a glass plate upright on the paper. This will serve as your plane mirror. Place a lit candle in front of the glass plate. You'll see its image appear behind the glass. If you look closely, you may notice two images of the candle, slightly separated. This happens because a glass plate has two reflective surfaces, the front surface and the back surface, and each one forms its own image. For this experiment, focus on the image formed by the front surface, the one closer to you. Next, take a second candle of the same shape, but unlit, and move it behind the glass plate until it visually overlaps with the image of the lit candle. When the two line up perfectly, you've located the position of the image. At that point, the object and the image are the same size. Trace the outline of the glass plate onto the paper so you know the exact position of the mirror. Mark the positions of both the lit candle and the unlit candle. Use a ruler to measure the distance from the lit candle to the mirror. Then measure the distance from the unlit candle, which marks the image position, to the mirror. So what's the relationship between the candle and its image? The image is the same size as the object. The image is the same distance behind the mirror as the object is in front of it. And the line connecting the object and its image is perpendicular to the mirror surface. In other words, the image formed by a plane mirror is the mirror symmetric counterpart of the object with respect to the mirror surface. There's no actual candle behind the mirror. So why does your brain think there is? A light source, let's call it S, sends out rays in all directions. Some of those rays hit the mirror and reflect into your eyes. Your brain assumes light travels in straight lines, so it traces those rays backwards. They appear to come from a point behind the mirror, a point we'll call S prime, the image of S. Because no real light is coming from S prime, we call this a virtual image. Plane mirrors have been around for a long time. Ancient people polished bronze to make mirrors. Today, mirrors are everywhere, from bathrooms to space telescopes. Dentists used tiny plane mirrors to examine teeth. Early military periscopes used two plane mirrors to let soldiers see the battlefield without exposing their heads to enemy fire. They're still used in tanks and submarines.
Bible, hit that machine gun. Look at your periscope. Periscope! Where are the carriers?
There she is.
We got a carrier, maybe 4,000 yards.
And when many plane mirrors are arranged in a specific pattern, they can reflect sunlight to a single point, the principle behind a solar power tower. Not all mirrors are flat. Concave and convex mirrors, together called spherical mirrors, show up in everyday life too. A stainless steel spoon is a perfect example. Its inner surface acts like a concave mirror, and its outer surface acts like a convex mirror. Convex mirrors are used in car rearview mirrors and safety mirrors because they expand the field of view. Concave mirrors are used in car headlights to make light rays travel in parallel. They also appear as cosmetic mirrors or magnifying mirrors because they enlarge images when the object is close. Large concave mirrors can even concentrate sunlight to boil water or cook food. And in solar furnaces, they can reach temperatures high enough to melt metal. Before we end this episode, let's look at one more demonstration. This box emits 3 parallel laser beams. When the beams strike a flat mirror, they reflect according to the law of reflection. This is specular reflection. Each beam bounces off at a predictable angle. Switch to a wavy surface, and the reflected beams spread out in different directions, breaking the clean pattern. This is diffuse reflection. With a concave surface, the reflected beams bend inward and converge at a focal point. With a convex surface, the beams diverge. If we extend those reflected rays backwards, they appear to meet at a focal point behind the mirror. This is Dr. Walton from Graceful Science. Thanks for watching.
Oh.